Hello, today in this video we're going to look at doing some spatial analyses on digital elevation models. We'll look at how to do these analyses in ArcGIS Pro as well as QGIS. And so this video is kind of designed for Lab 2 of geomorphology in spring 2023, but it can be applied to advanced GIS or intro to GIS students as well. So in this class, we have in Lab 2, we're looking at the Stockton Bar, which is a certain place in Utah just south of the Great Salt Lake near Tooele. So it's this kind of landform associated with prehistoric Lake Bonneville. And the landform is a sandbar. It's actually two sandbars that actually divide Rush Valley from Great Salt Lake Valley to the north. And basically what was going on at the time is there was a big lake, right? A big pluvial lake of the Lake Pleistocene time. And in the wintertime, kind of the biggest winds would come from the northwest across this huge fetch of the lake for 100 plus kilometers, drive big waves and circulation that would kind of run up against the Ochre Mountains, which are here to our right, and then kind of send water along these mountains and down and around. And so all the way, the waves were washing up and pulling back, washing up and pulling back sediment and carrying it along and then depositing it and building this big sandbar, which we can see has holes in it, and it's being mined for gravels today. And so for this class, we want to use digital elevation models, which are basically digital raster data about the Earth's surface elevation. We're going to compare these models and how they can be utilized to visualize the landscape and geomorphology. So this is our first experience with that in this class. So it's a kind of baseline tutorial. So in our folder in the GIS drive, we have some data already. So as you're working, you might want to save your work locally and then move it in a file that you create for yourself in our GIS drive. So if you go back, maybe you create a folder here within students where you can save this work too. And I'll make one for myself out here, which I'll call Dr. Tokay files. Okay. So to add data to ArcGIS Pro, there's a bunch of ways you can do it. So you could, if you knew what you were doing, drag the files from Lab 2. If we go into here, we could find the right file. Like if I knew that this LiDAR TIFF was the right file, I could drag it over. But I don't really know that fully. So it might be better to go over up here into the menu pane and choose to add the catalog pane over here. And then within the catalog pane, we can add folders that we connect to. So I'm going to add a folder connection to our GIS drive, which is within this PC, our geomorphology drive, geomorphology labs. Say OK. So now I can navigate into Lab 2, into the Stockton Bar data, and you'll see that they start to look like more simple files. So the .tiff files are DEMs, but in this case a lot of the work has been done for you. So there's some subtraction files out here, and then within these folders here there's the DEMs for LiDAR data, high resolution, I believe 1 meter resolution, national elevation data set, which is older 10-meter data, and that comes from contour lines, whereas LiDAR comes from point clouds of lasers, and it's been filtered, I think, to bare Earth. SRTM is Shuttle Radar Topography Mission, and that'll be 30-meter pixels. And then this other one, AGRC Autocorrelated, is based upon imagery and stereo imagery, and that makes a 5-meter digital elevation model for the state of Utah. ArcGIS is from 2007. The LiDAR was, I think, from 2014. The NED is processed from data that was produced before 2004, and the SRTM, I believe, is coming from 1990s, like 1998, flown from the space shuttle. The SRTM and the ArcGIS, because they're coming from radar in one case and air photos in another, they bounce off of the data, the reflected light, or the radar is bouncing off whatever's on the Earth's surface. So they're not bare Earth models. They would be thought of as a digital surface model of the Earth, not a digital terrain model. The NED is from contour maps, and the LiDAR is from point clouds, hopefully filtered to bare Earth, so they might be better thought of as digital terrain models. And so if we were to difference them, we might see differences due to trees in one image and no trees in another for some of them. So keep that in mind. Okay, so let's go ahead and open up one of these folders, and in there you'll see that there's a slope map for ArcGIS and a bar clip map. The bar clip is the data clipped to the Stockton bar, so let's drag that in. And then we can see that digital elevation model appear. And if we can sort of sense the topography under there, basically it's each pixel in here. If we zoom in, we can maybe see the pixelation. Each pixel, the values of that pixel, there's only one band, and the band is tuned to elevation for a DEM. And so we can see they range from 1484.1 to 2244.7, and those values are not in feet clearly because we sit nearly 5,000 feet above sea level, so those must be in meters. So I can add another, in this case, let's add a LiDAR bar clip. So it's clipped to the Stockton bar. Put that on top. And we may have seen that the pixelation, you have to zoom way in to see pixels. So it's a much finer resolution. And then let's get the NED. And let's get the SRTM. So keep adding the bar clips. And let's put them in order of resolution. So LiDAR is the most fine resolution. ArcGIS is the next most fine. Then the NED, I'll put that below that, and I'll put the SRTM on the bottom. So if I turn off the better ones and look at the SRTM, we should see that it looks quite pixelated if we get zoomed in. Yeah. Okay, so we've got our DEMs open. So that's great. And we can make other visualization products from these. And some of them I've given to you here. I can see that I've made a slope map for each of these data sets. And also in the LiDAR tool folder, there's aspect map. But in the lab, I also ask you to make hillshades, and you might even consider making a curvature map. Although it's not required for this lab. Let me show you a few examples of these, and then you can make your own for the ones where they're not existing. So for the NED, we can see that there's hillshade, NED HS, hillshade 180 and 315. These are different sun angles. Let me add one to show you. So there's our national elevation data hillshade model. And so it has a 315-degree sun angle, which is from the northwest. So we can see that any slopes that were facing the northwest are illuminated, and ones that are facing the southeast are in shadow. So it's modeling shadows across a landscape to show us topography. So hillshade is a very valuable visualization product. I'm going to pull in now a slope map for the NED. And we can see this looks different. Its values, if we look over, are not the same as hillshade. Hillshade is like value of brightness. And NED slope is values from 0 to 55.9. So the steepest slopes in the NED are 55.9 degrees, and they show up in the way we have it now as white, and low slopes are showing as dark. That's actually not what we want. We want to change this to a slope shade map, which will mimic somewhat the hill shade. So right click on the slope map and go to symbology. And we can basically just invert the color scheme so that then the light colored slopes will look, the flat areas will be light and the steep areas will be dark. So it doesn't look the same as the hill shade, but it looks similar. Hopefully you see that. Can kind of interpolate it in your mind similarly. We can see where channels are, flat geomorphic surfaces, steep escarpments because of the lake shore washing across, or the edge of the spit or bar. So that's our slope shade map and our hill shade map. Let's move those down kind of with NED. I can show you a little hint actually too. We can actually make group layers. If we right click on our map, we can say make new group layer, and I could say call that NED, right? And I could kind of put that here and move my bar clip, my hill shade, and my slope map into it if I wanted. And then if I want to turn them off and on, I can do it as a group, or I can open it up and adjust how I want otherwise. That's one kind of little tool you can use to organize yourself in your map. You could also, instead of filing it as a folder for NED, you could file it as a folder for slope maps or hill shades. Whatever you think is better for you. Okay, so let's give you one more interesting feature to look at. So let's add in the aspect map. In this case, the only one we have is for LiDAR. So it's going to be wild. It's got to build some pyramids. Guess they were not built. Okay, so the values of aspect we can see are coming from basically 0 to 360. So it's 360 degrees around the different azimuths of 360 degree circle. So it's just showing us what direction the slope faces. Does it face 0 degrees, 1 degree, 90 degrees to the east, 180 to the south, etc. And so you can kind of sense that the way it's colored now, it's just from white in the north to black also in the north, interestingly. That's not a great way to visualize aspect. Usually when you make an aspect map, we'll do that in a minute, there's kind of a default way that they show it, which is classified it as like quadrants or octants of is the sun coming from the northeast or the northwest, etc., classified like that. But actually, for LiDAR visualizations, if you're using a slope shade map, combining that with an aspect map can be really helpful. And so a stretched aspect map. But what we want to do is stretch it with more colors so we can see more variation. And I find that optimal stretch could be like going between 3 colors. So here we go, green to light to something else. That could work. Or, you know, see here we're going maybe even across more than 3 colors. That might be decent, but it's a little bit too psychedelic for my taste. So that's why I like the 3 colors, and kind of natural colors would be ideal. Let's see what we can choose here. So we could go this red to kind of dark. Nah, not my favorite. Let's see what we got up top here. Yeah, let's do this kind of green to kind of, oh, that's more than 3 colors. I got to find something else. Here we go. Okay, so why is that a good choice? It gets a little funky in some places, but let's zoom in here. And so where are we? Let's turn on our let's turn on something else. We need our slope map, so I'm going to add that on top. Okay, so this is a LiDAR slope map. I need to invert these. So go back to symbology, invert. Okay, boom. Okay, so now I'm looking at LiDAR. I'm going to turn off NED. I'm going to turn off SRTM. And so we're just looking at the LiDAR data, and we're looking at the derivative product of slope on top. And so we can see really nicely that steep escarpment where the waves of Lake Bonneville are washing up against this alluvial fan and pulling material away. If I turn that off, the escarpment almost disappears, but some other things stand out. So hopefully you see that some fan structures, right, where you change aspect across different surfaces of the fan show up kind of nicely in that data. And you can see some of the details of the alluvial fan in the aspect map. So what I like to do is actually make these kind of transparent over each other. So to make an image transparent in ArcGIS Pro, we'd click on it, go to imagery, appearance, not imagery, and go to transparency. Whatever we're selected will become the transparency we tell it. So we make it 40% transparent. Then I can see the kind of details of the slope, and I can also see these alluvial fan piles going off in the distance. One thing I can see right away from this is that this LiDAR data is not a bare earth model. It is a surface model. And so we can see patches of trees and things as well. Oh, look at that. There seems to be a fault scarp up here in the hills. That must be the ochre fault. Anyways, so hopefully this shows you nicely that we can see really great details in these maps in the LiDAR data. Compare that to SRTM slope map, which I'll add on top of here just for comparison. Woo! Not much to see there. Yeah, really coarse, 30 meter versus what pixel size do we have? Zoom in and find out. So actually, we don't have to zoom in to find out. We can right click, go to properties, and go to source, and go to spatial reference. Scroll down. We can see what is the coordinate system, the projection, and the units. So it's in meters. And yeah, I believe it is a 1 meter pixel is what that is saying. Okay. So how would we make these different products that I've been showing you? The way to do that is to go to analysis, and we would do analyses, what's called spatial analyses on the digital elevation models. So we go to analysis, go to tools, and then it tries to default you to search for the tool that you want, which is a great way to go. Like I can write, I want to make hillshade, so I can write hillshade. And some tools come up that look about right. There's one in 3D Analyst tools and one in Spatial Analyst tools. The one in either of these will work. Usually I direct students to go to Spatial Analyst tools. If you don't find what you want right away, I think you can click on Spatial Analyst tools. It'll take you there. It'll show you where that lies. There it is, hillshade. And look what else is in here. Aspect, so that'll make us our aspect map. Slope, that'll make us our slope map. Curvature, curvature map. Contours, etc. So that's all here under Spatial Analyst Tools and Surface. So yeah, we just click on the hillshade, and then whatever raster we wanted to make a hillshade model from, we would choose it. And it's important whenever you're making these derivative surface products that you choose a DEM and the correct DEM to make the surface product from. So in the case of SRTM is going to be quick. I can make the hillshade from that. Again, I recommend that you basically you could either save this in your geomorphology labs folder, or you could work in your documents and then at the end of the day move there. And that's what I recommend. So I'm gonna do that. So I'm going to create a folder which I'll call Geomorphology Lab 2, and I'm going to save my raster there. And this is important. I always recommend saving the raster type as TIFF. So I call it SRTM. Capitals aren't important, but and then I'm going to call it hillshade.TIFF. TIF. And then you have some choices to make. Azimuth is the direction the sun will come from. Altitude will be the kind of the angle of the sun. This is the default, and that's fine. I asked you in the lab, I think, to model it after the air photo that I provided. So think about that. Z factor can be important, and it seems to be telling me that it is, because the output geographical spatial reference are undefined. A default Z factor of 1 was used. So if it's a geographic coordinates, it needs a Z factor because it's doing trigonometry, but it's not using meters by meters by meters. It's degrees by degrees by meters. And so then we would need to convert that. I think we're going to get an error, but let's check it out and see. It looks okay, but not great. And I think, yeah, there's a Z factor error there. And so then to solve that, you could do one of two things. You could either convert your coordinate system to a UTM projected coordinate system, so your horizontal units would then be meters, just like your vertical units. That would require no Z factor. Or you could go to a table and look up the Z factor to apply to a geographic coordinate system at the latitude that you're at. And that will make it look okay for the hillshade. So please do that. So I believe you can just Google search that. But just to give you another example that maybe shouldn't have this problem, I can do this same sort of analysis, but I can choose one that's already in the correct coordinate system. So I think a LiDAR coordinate system should work, and it should be in the coordinate system we want. So I'm going to call it LiDAR hillshade.tiff. Save. Let's try again. We didn't get any Z factor error this time. It knows that we're in an appropriate coordinate system for doing trigonometry. Ooh, that's pretty satisfying to look at. This hillshade map is quite good. We can see really interesting structures, maybe like where different backhoes have like scraped at the, and we can see kind of a beautiful landscape, basically. Then it ends. Cool. Okay, so yeah, if you want to make hillshades, that's here. Contour maps, curvature maps, aspect map, and slope map are all within Spatial Analyst tools. Another thing I asked you to do in this lab is to make profile tools. And a common problem in ArcGIS Pro is that students will go under these ready-to-use tools and see this profile tool. And to use that, a couple things. You need to sign in to your account. And the reason for that is it's asking to use online data from the cloud. And that's not really what we want to be doing, okay? We want to be profiling the landscape or the digital elevation models and comparing them. And I did post a way that you can do that. To do that in ArcGIS Pro without purchasing outside tools, you need to use 3D Analyst tools. And basically what you need to do is make the lines that you want to profile across your image. And then you need to intersect those lines to make them 3D features. And then from that, you can draw a profile. It's cumbersome. I'm going to show you two other ways that you can do it. That way is articulated in a tutorial posted to Canvas or linked to your lab. The other ways are to use different tools, different software programs. And the best one that we have, and it's also nice because it's free, and so I'd encourage you to use it. You should have it installed on all our computers. You probably have a different version than me, but let's just open up something called QGIS. So QGIS is an open source graphical user interface GIS program. It's open source, so anybody can contribute to the tools that are built in here. It's maintained by a group through donations. It has so much functionality, and many of that functionality is more customized, and in some cases better than some of the things you find in the ArcGIS Pro. That being said, sometimes some of the tools aren't as stable, and you may run into issues. But generally speaking, it works really well for these simple things that we're going to do in geomorphology class. So if we went into our geomorphology drive, right, we can add data by connecting to it. And you can see right up here, as it opens up, I've done that already. So I could find geomorphology labs, go to lab 2, Stockton bar data, and bring things in like that. If you're clever, you can navigate through here and just drag and drop. So if I want the LiDAR data, just drag it in and drop it. It shows up. There's no default base map in here. But so here my LiDAR appeared. It's wonderful. Let me just first show you right away. There's this cool profile tool where you can just basically say, okay, what does the bar look like? Click across it. Oh, nothing showed up because I need to add a layer. So whatever layer I click on, I click add layer. Boom. It shows you where in the profile you are and what the profile looks like. It's very clever. It gets better. So if we added another data set, so like if we wanted to look at not just the LiDAR, but let's look how LiDAR compares to the really coarse SRTM. I'll add that. So SRTM is now confused because it's a different coordinate system. So that there was some transformation there. It's probably going to have some issues related to that. But let's add this as well, and we can change the color. SRTM can be blue, and so hopefully you're not red-green colorblind, or red, well, I guess that should work, so it's blue. So you can see the blue is SRTM. It doesn't see the low point very well here. Kind of maybe it's just not seeing like some of the detailed structures of the bar. It's kind of very smooth, and that's because it's 30-meter pixels. It should be smoothed. Okay, but hopefully you see that this is really valuable, right? These profile tools, looking at a 2D profile of our digital elevation models is like a fundamental thing in geomorphology, and so QGIS is the best in terms of these tools for that. I'll add in the NAD, and I will add in the ArcGIS as well, and I'm going to add them on here, and I change the color of the ArcGIS to black. Okay, and click on the NAD, add that, can change that to pink. So now if we zoom in, what do we see? We can make this bigger. So we can see that the NAD is kind of awful in some parts of the bar, and actually it doesn't seem to be doing as good a job maybe as the SRTM in depicting the bar. But the ArcGIS, actually the 5-meter data kind of shows you some of the details of the Stockton bar that is obviously going to be shown better in the LiDAR, although the LiDAR is not as smooth, and that could be because it's not fully ground data. It also has bushes. Yeah. So we can, do this wherever we want, which is quite useful. Of course, to draw profiles, it can be really nice to have some better visualization than the DEM. The DEM sort of shows you what the topography is, but those visualization products are much better. So we'd want to pull in, like, the LiDAR hillshade would be the best. Probably have one of these sitting around here somewhere. Oh, let's make one because I wanted to show you how to do that anyways. So if we go view, where is it hiding? We want to, it's not view. We want to see another pane. Let's see. Toolbox. So if we go under processing, click toolbox. So it's just like ArcGIS in that sense. There's a search tool here. You can say, I want to do a hillshade. And look, don't even have to finish typing. Raster terrain analysis. This function is provided by QGIS because you can see that Q symbol. There's other choices. Saga GIS, which is another open source program. GDAL. These are all available in here. It pulls in different open source into QGIS, different algorithms that have been written to model hillshade. But I generally go with the natively supported QGIS one. It's probably going to work the most stable. It's most recent. Okay, so I want to do hillshade on the bar clip. Z factor of 1 because we're not changing coordinate systems. Its default azimuth is a little different than ArcGIS, but that sounds good. I'm going to run that. I didn't say to where to save it, did I? Finished, and it's there, but it's hiding. Okay. Wait, what did I? Let's go back to parameters. It's not looking that good. LiDAR bar clip. Hopefully you see it kind of looks more like the hillshade of a much coarser data set. Let's save it to a file. And QGIS.tiff. We can always pull that other one in if we don't like this, but it should work better. LiDAR bar clip, input. We might need to choose something about the file size. Like, do we need to tell it to not be too simplified? I'm not seeing that option in here. In terms of what is the grid scale. Well, let's try to run it again and see what happens here. Running. Oh, that looks better. Okay, so I don't know if it's because we did it as temporary file before or what, but yeah, that's a good looking hillshade. Okay, good. So yeah, you can see it's pretty simple, just as easy as any other program to run these. The cool thing now, we can look here and we can then go click our terrain profile and we could say, oh, I want to profile this alluvial fan that I think is sitting here. And so I'll go along this road. And boom, there, I'm going over, let's pay attention to the red, which is the LiDAR. I'm going over that alluvial fan. Can even identify where the channel, the most recently active channel is, sitting in there, high up on the middle of the fan, coming out of that valley. And then you can see the slopes of the fan over here. It's very cool. The ArcGIS is sitting uniformly higher throughout there by quite a bit, surprisingly. Much different than in the bar itself. It's kind of curious. And then the other data, yeah, they all are different representations. They're all models of the Earth. Let's check it out right here across this channel. You can see they're all representing the channel differently. The ArcGIS seems to be a little shifted on one side and not so much on the other. So it's probably seeing the trees even more than the LiDAR surface model. The SRTM barely saw the channel because it's so small. And NED saw the channel fine, but actually it's kind of exaggerated. And then if we go across this big geomorphic surface between these two channels, we can see that nice surface playing out, but we can definitely pick up what the surface really truly looks like a lot better with that red LiDAR data. And so, yeah, I really would encourage you for profile analyses to use QGIS. Okay, so the cool thing about this is we can save this after the fact if we want, and you could do some kind of analyses if you wanted on it. Really very cool. One final thing I'll show you is a difference map. I've already made some of these, so I'll pull one in that way for you to see. So if we go to our folder, I can just drag it in there. So you might have been noticing that there's these LiDAR minus ArcGIS, LiDAR minus NED, LiDAR minus SRTM. Since the LiDAR and the ArcGIS are kind of closest in time and resolution, we'll do that one. So the ArcGIS was a data set made in 2007. So in the LiDAR about 2014 or 15. 7 or 8 years of difference in topography. Basically, I subtracted one from the other. I'm going to add that here so we can see it. And so you can see basically where there's difference in the landscape. And so if we turn that off, we can see that right here, there's this big black area. Black in the is a negative value, -30 at the peak. So that means that the landscape went down 30 meters. So that's a huge quarry excavation, if it's indeed 30. We could profile it and find out. So we click the profile tool again. And then we click the add layer. We can see, yeah, excavation, -30 meters. Now, that's not the same. It's not 30 meters below sea level. It's 30 meters of change negatively. But then in other places, we can see piles, right? So there's a big pile of sediment right there and a big excavation here. So we excavate from the gravel pit, put the pile there, and then we can truck it away and use it in development. So we can see where there's been landscape change, and a lot of it has to do with mining. But you might see some hints of dark, remember, is excavation, or it's gotten lower in the channels here, but remember that could be due to seeing more tree or less tree with the LiDAR. Less tree with the LiDAR than the ArcGIS. But if we go to this area here, which is like this steep slope that the trains go through, we see some differences there. Let's see what that's about. So we see greater elevation, so positive relief on one side and negative relief on another. And so, that does sound to me like a tree factor, right? Because one side, something doesn't seem quite right. Or it could be a vertical shift. So if one of the data sets is off just slightly in an east-west sense, the hill could be shifted over. So then one side of the hill valley could be positive change and the other side could be a negative change. And so that's another thing to worry about when vertically subtracting the coordinate systems or the different data, is whether or not the coordinate systems are really truly matched up to begin with. Otherwise, we'll end up getting kind of a hillshade effect out of the subtraction. And actually, we can sort of see that in here. We can see where channels are. And so I do think that we have a little bit of a misfit of the data, and that could just come from the resolution of the data as well as a possible shift in the pixels. But nevertheless, we can do these subtractions. And if you wanted to do that yourself in here, in ArcGIS, it's called raster calculator. Let's see if we can find a calculator here. So raster analysis, raster calculator, boom. Yeah, so we can open this up a bit more, right? We could say, I want to subtract, I want to take the SRTM away from that. And so I'm going to run that. Oh, I failed because I didn't tell it too much. Cell size. We want it to be the cell size of, I don't know, the SRTM, I guess, 30 meters. Let's run it. No reference layer selected, or see it. Or coordinate system. Okay, reference layer, output extent. Okay, they can just choose that output. Okay, what coordinate system? Say in the UTM, run. Zoom to layer. Oh, so I kept it a little bit there. So we can see some differences through there. We could profile through those differences. If we add that layer in, turn this one off, change the color. So there's some areas that the SRTM what was it? It was NED minus SRTM. So the SRTM is way higher than the NED. And remember, it was a radar image, so it could have reflected off something taller rather than representing the ground surface. So that makes sense. It could be negative. We should probably broadly be negative across the image in that sense. But yeah, so hopefully you see that QGIS is a really cool and useful tool, and hopefully this helps you get started with DEM analyses generally and profiles as well.